Welcome to the presentation of this demonstration entitled Augmented Reality with Perceived Zero Latency. This work has been developed in the context of the Desire 6G European project and includes the collaboration of several partners. Augmented reality enables the visualization of a remote scene with different viewpoints highlighting specific objects and artifacts for improved situation awareness. In this use case, in the forward chain, videos are streamed by mobile user equipments and locally elaborated to classify target objects. Then, streams are further elaborated at the edge to provide data fusion. The results is sent to the end user wearing a headset, in charge of the augmented 3D reconstruction. In the backward chain, the user sends commands to the source to change the scene visualization. The use case scope is conceived for enhanced surveillance and rescue operations in hostile environments. The workflow requires stringent latency constraints to assure interactive quality of experience. The first demo objective is to showcase a service-oriented end-to-end pervasive monitoring system, where actual end-to-end latency experienced by the application is monitored constantly in different technological domains, and where programmable data plane enables in-band telemetry collection of metadata. The second objective is to demonstrate service reoptimization at near real-time using the multi-agent system concept, in charge of receiving, aggregating and analyzing telemetry in a distributed way, in order to detect service-level agreement violations and suggest the most appropriate countermeasures. The setup of this demo includes hardware and software resources of a federated testbed, including the Arno testbed and the UPC testbed. The Arno testbed hosts a user equipment, a RAN site, a programmable packet optical network and an edge site, while the UPC testbed hosts the MUS agents responsible for the AI-based reoptimization. The UE is a NVIDIA Jetson Orin board equipped with video camera and a Quectel 5G modem to enable 5G connectivity to the RAN. The RAN radio unit utilizes 4 radio channels using coaxial cables to avoid interferences, connected to the DU with a 10G interface. The Accelerin DU software is deployed in server S1, while the CU runs in server S2, connected with a 40 gigabit Ethernet interface. S2 includes the near real-time RIC and the Open 5G core network. The Metro data plane is powered by 4P4 NICs switches deployed on Dell servers using eBPF acceleration, connected with 100G interfaces. The switches run extended in-band telemetry and a 2-stage P4 collector for reports capture and latency statistics extraction. One link includes an optical bypass realized using 2 Ericsson ROADMs, equipped with coherent tunable cards. The first node implements a congestion programmer using the hardware queues of a Juniper router to emulate real bottlenecks. The setup includes a Spirent traffic generator, a GRE tunnel connectivity and the MUS agents deployed at the UPC testbed. An augmented reality use case is considered. Video sources originated at different angles and sensors are sent to intermediate AI-based processing stages to detect and add video artifacts. Data fusion allows for 3D reconstruction for the end user wearing a 3D headset. A forward chain is used to elaborate and send AR data to the headset, while a backward chain sends commands to the sensors to change the video features in real time. The forward chain of the application developed for the demo is conceptually shown here. The source app runs in the user equipment and performs video capture and first object detection. Then, augmented data are sent to the edge app before further data fusion and a second detection. Final data are streamed to the Meta Oculus for 3D vision. In our current developmental phase, we leverage the YOLO library for object detection. To guarantee a real-time quality of experience, it is necessary that the one-way end-to-end latency is kept under 25 milliseconds. The use case is mapped to the preliminary application development. In this release, the source processing runs object detection using the YOLO library version 7, while the Edge app performs AI-based pose estimation resorting to the OpenPose library. The result of the artifacts introduced by the two processing stages is shown in this video performed during the last EUCNC 2024 conference, where we invited the Desire 6G booth visitors to wear the Oculus and try the live application. The Oculus, a virtual reality device configured in pass-through mode, displays the area surrounding the user captured by its stereo camera, then overlays information about detected objects behind obstacles. In fact, the camera is able to capture images to detect objects occluded in the user's field of view. The green bounding box represent detected people, while red artifacts their current pose. We start the demo showing the Accelerant RAN deployment. The CU, the near real-time RIC and the CN are deployed at Bootstrap, while the DU and the radio unit are deployed by the RAN operator. The Dirac dashboard includes the automatic scripts to deploy all the disaggregated RAN modules independently. The UE is attached to the RAN using a registration script. The dashboard shows the current topology including the attached user equipments. A rich monitoring Grafana section is available in the dashboard, including many metrics such as throughput and radio quality of transmission. The statistics are reported both in aggregate and per user equipment way, offering an effective real-time monitoring of the RAN performance. In Workflow 0 we show the steady state and the pervasive monitoring using in-band telemetry. Video packets are timestamped at the UE and at the CN to obtain the RAN latency. Once entering the packet optical domain, each node adds its hop latency to obtain the second segment latency. At N4, packet is propped to be delivered to the edge app and a report is generated towards the P4 collector. Packet metadata are stored and processed here. After a timeout, a stats report message is sent to the MAS agent that checks the SLA compliancy. This real-time pervasive monitoring operates at the single packet level and is able to detect and localize latency deviations with the finest granularity. The MAS agents operate at near real-time, resorting to the telemetry statistics provided by the P4 collector at each stats report generation, in the order of tens of milliseconds. The agents are able to identify the most appropriate countermeasures to recover the SLA requirements in case of latency deviations. Now, we deploy the RAN and the application. The DU is deployed by the operator in the dashboard. The user equipment starts the attachment procedure towards the DU. The AR application at the source node starts to perform object detection, and the result video with artifacts is sent to the edge node. These are the latency plots extracted from the collector and monitored by the MAS agents. The total end-to-end latency is below 25 milliseconds, meaning that the SLA requirements are met. The Wireshark capture at the collector shows the telemetry reports received and processed, along with the report summary, generated towards the MAS agent each 16 report packets. In such steady-state conditions, the application performs regularly. If we inject an external traffic flow from node N1 to N4, a congestion will occur in the first interface queue, with a latency increase in the order of tens of milliseconds. This produces some video lags at the end user. When the external traffic is stopped, steady state is recovered. The latency violation shown here occurs since the MAS agent has been deactivated. In Workflow 1, we create a switch congestion and activate the MAS agent to suggest the recovery procedure. We start with steady-state conditions. Then, we start the traffic generator with a flow traversing N1 and N2. Congestion occurs at N1. The MAS agent detects an SLA violation in the packet optical segment and suggests a rerouting of the application flow through a backup path. The underlying SDN controller enforces this flow rule to N1. Traffic is diverted. End-to-end latency is reduced due to congestion avoidance. In this way, the SLA is fully recovered. Let's see the workflow in action. In Node N1, the initial flow rule policy sends all the application traffic along Node N2 using the first path. Now, external traffic generator is started. The Grafana dashboard at the P4 collector shows the traffic switched from path 1 to path 3, the optical bypass in this case. A slight latency increase is reported in the first path, this because the latency statistics are averaged over the summary packet window, and the mass is fast enough to suggest the rerouting. The Wireshark capture at the MUS agent shows that the suggestion response time performed by the module is below 1 second. In Workflow 2, we induce a latency increase at the RAN centralized unit and enable the MUS to trigger reoptimization. The same steady-state conditions are configured. Then, we configure an extra delay on the interface between the CU and the CNVMs. The RAN latency detected via telemetry increases. The MUS agents detect the SLA violation in the RAN segment and suggest to drastically reduce the latency in the packet optical domain, thus activating the optical bypass. The underlying SDN controller enforces this flow rule to N1. Traffic is diverted to the bypass and the SLA is recovered, even in presence of an extra delay at the CU. And let's see this last workflow in action. We start the RAN delay script. This script configures a fixed additional delay to all packets traversing the CU and destined to the CN through a Linux TC configuration. The Grafana dashboard at the P4 collector shows the traffic switched from path 1 to the optical bypass. The latency increase in the RAN is in the order of 9 milliseconds, while the latency reduction in the PDP segment is around 5 milliseconds. Because we avoid the hop latency introduced by intermediate P4 nodes. Hence, after recovery, we measure 22 milliseconds of end-to-end latency, again under the SLA threshold. Looking at the measured end-to-end latency budget, we validate that in both the congestion workflows, once triggered the MUS reoptimization, the system is able to restore the latency under the threshold. In the switch congestion case, the MUS can select between two path rerouting alternatives, while in the RAN congestion case, the optical bypass is the only one guaranteeing the SLA, thanks to its low latency under 1 millisecond. In conclusion, we have presented a demonstration of augmented reality use case requiring low latency service level agreement. Two Desire 6G innovative pillars, the pervasive monitoring based on data plane programmability, and the innovative AI-based MUS agent, are able to detect and localize latency deviations, while suggesting and enforcing the most suitable countermeasures at the different segments of the network infrastructure.